But now, ladies and gentlemen, we come to the main broken point this afternoon. As you know, our university is embarking to expand its mission by also increasing its presence in science and engineering with some very exciting projects and some very exciting developments. In 1916, Albert Einstein originally presented the existence of gravitational waves, adding that they probably would be very, very hard to detect. 100 years later, our next speaker has really been presenting with his colleagues the first observation of gravitational waves ever, a major scientific event and a major scientific breakthrough. He is a co-founder and former director of the United States National Facility for Gravitational Wave Research, LIGO, which managed to do what Einstein himself doubted was possible. 1 year later, he took a plane to Stockholm to receive the medal every scientist secretly dreams about. We are honored to have this Nobel Laureate here today to introduce us to the fascinating field of research. Please give him a big applause, Professor Barry Barish.
Good afternoon. Thank you first, Professor Paul, for inviting me today. Sorry for the hoarse voice. For inviting me today and for your thoughtful presentation earlier. I've never seen an event like this, so it's very interesting for me to be here. The first day of the academic year at Caltech, where I teach, or the University of California, where I also teach, I think is a day of anxiety. Our students are trying to make sure they get the professor they want, or the class they want, or are worried about something else, or the books and so forth. And having a celebratory beginning of the year is something we don't experience anywhere that I know of in the US. But I think it taught me something which I'll explain to you, and that is, instead, we seem to have something at the end of the year, which is celebrating, of course, the end of the academic year and graduation. And we give it a name. We call it commencement, which always bothered me because commencement means beginning and not the end. And so I suspect now, somebody can correct me, that like a lot of things, we borrowed the idea from Europe and then turned it on its head, which is often done in the US. And now we have our commencement at the end of the year. So anyway, I'm going to take you on a tour today of the discovery of gravitational waves. I mean it for a broad audience. So I'm going to try to tell you some of the challenges that it involved and some of the history so you can understand a little bit how science develops. And there's just a couple places where I may have slides that are a little bit difficult, purposely aimed for a few of you that understand more, but that shouldn't trouble you. I'll warn you. So I'm going to talk about, first, the title is very futuristic, and that's where I want to end, and that is that, yes, we discovered gravitational waves, which I'll spend most of my time on, but the real future is how to probe the universe in a completely new way, which is with gravitational waves. So let's begin with something we all learned when we were really young, and that's something about gravity. What we were taught came from the guy on the left, and that's Sir Isaac Newton. And all of us in elementary school learned gravity from Isaac Newton. In fact, it is probably or arguably the most successful theory, not just of gravity, but the physics theory of all time. It was written in the Principia in 1680s and survived for more than 200 years. It's not wrong. I'll come to why a more sophisticated theory of gravity was needed and when Einstein came along. So he taught us gravity. And he taught us gravity by giving us what happens if you have two massive objects and they're some distance apart. And most of us at some point saw a formula, which is that the force that attracts these two is proportional to the product of the two masses. and inversely proportional to the square of how far apart they are. Newton also, in the Principia, goes through all the calculus to show that you can actually pick the center of gravity of each of them and measure this distance that I show here. That theory explained everything about gravity for more than 200 years, including the orbit of the moon around the Earth around the sun, why we have tides, and so forth and so on, what happens when the apple falls from the tree. All of it worked, almost all of it. Then Einstein came along. I give you not because you'll understand it, but because there's also a formula, a little bit more complicated, that Einstein gave in 1915. This is 1 year before gravitational waves. This is his theory of gravity. It's often called the theory of general relativity. He developed it after he had developed the theory of relativity, and you might wonder why. After 200 years, we have a theory of gravity that worked for essentially everything, except one puzzle, which I'll bring out, which was a small deviation. And yet he brought on a theory that solved two issues which don't matter for much of that, but matter. And the first one I'll describe in a little bit and tell you why. But a theme that I want to have today is looking forward. And if we look at what I said for my title, Probing the Universe, I want to look at 20th century first, astronomy, and how it moved forward. And the way it moved forward, the biggest leap in the last half of the last century was to do astronomy not just looking at light that we see with our eyes, but looking at electromagnetic radiation in all the different wavelengths, from radio waves, which are very long wavelength, to gamma rays, which are high energy particles, or short wavelength, and looking at the same objects with that. And in this illustration, we look at a sophisticated object, the Crab Nebulae, which is studied in all the different wavelengths. The different images are instruments that look in the different wavelengths. And it's that ability to look at some phenomenon in the universe and study it in different ways that had made such great strides in astronomy that you read out about all the time in the last half of the last century. As we've moved into this century, there's another addition that's been made in astronomy, which I'll use as the analogy first, and that is the ability to combine instruments. And we all saw that this last spring. In the US, there was a big picture on the front of the New York Times of the first image ever of a black hole. That was something that's happened after many years, but a very big advance in how we do science, and that is to combine the information from instruments around the world. There were 6 radio telescopes in different parts of the world, not made to be used together, but through a lot of hard work and creative ideas, they were able to be brought together to make one instrument that was more or less the size of the Earth instead of the size of these instruments. And that enabled them to image a black hole. So astronomy has developed, and it's my analogy, as we've learned how to not just do what Galileo did, look through a telescope and look at optical light, but get advanced instruments, which helped us, and then learned how to bring them together. And the same theme is going to apply in gravitational waves, as I'll show. So the next frontier in astronomy is what we call multi-messenger astronomy. And that's to combine astronomy, as I've just shown it, with other probes that'll give us even more information about anything that happens in the universe. In astronomy, we have all these different satellites or instruments on the Earth, and they look at all the different wavelengths, which I've illustrated before and here. Secondly, we have another way to look at the same objects, or some of the same objects, and that's with gravitational waves. This is photographs from the sky of the 2 gravitational wave instruments that we have in the US, LIGO. one in the state of Louisiana and one in the state of Washington. I'll talk about them in a little bit. The third probe that one could use to study the universe, so this is the ultimate way to do it, is to also use particles that are emitted from any object in the universe. And you need one that'll go straight. The only other one that'll follow the path of going straight from where it was emitted, other than the photon, which is light, which we're already studying, is neutrinos. So there's a big effort to also detect neutrinos from any object in the sky. And this is a photograph, or this is a figure of a very ambitious way to do that, which is being done at the South Pole, called Ice Cube, obviously an appropriate name for the South Pole. And there they've basically taken hot water, drilled holes down deep into the ice, where the ice is very pure, and then put photodetectors in these strings that are shown here and detected these high-energy neutrino particles. So as we move into the future, I think we'll see in steps astronomy taking this further leap of not just using electromagnetic instruments, but using gravitational waves, which I'll show you we already are starting to do, and neutrinos. So let's talk about gravitational waves, or gravity. So Einstein came along and made a new theory of gravity. And that new theory of gravity basically describes why the apple falls from the tree, or why you get the orbits of the moon around the Earth, and so forth and so on, but also describes what happens when those objects are moving very fast, and so forth. This is a picture of gravitational waves, which I'll circle around to, which happens just like electromagnetic radiation comes whenever you have what we call a dipole, two charges oscillating, make an electromagnetic wave. Here you get a gravitational wave when two objects circle each other and lose energy by gravitational radiation. And so that's a picture of what makes it. Those two objects, in our case, were what are called black holes, which I'll describe. This is my only hard slide, so you can ignore it if you want. But I feel compelled to show that gravitational waves give what we learn in physics as the wave equation. So if you take general relativity, I define how I do it on the left, you get an equation which has different letters, but for those of you that have studied physics, looks like the wave equation. The wave equation then gives traveling waves that are shown here, just like in electromagnetism. Only the two waves in electromagnetism are perpendicular to each other, and here they're at 45 degrees to each other. And that's because gravity has what we call spin 2. That's the most theoretical thing I'll say today. So that's gravitational waves moving along, and that's what we want to detect. Let me reflect for a second on why we need this theory and what it does for us. So the problem with Newton's theory of gravity are two. One is that when the apple falls out of the tree, in Newton's theory, you see it immediately. That doesn't matter. Of course, that's okay. But in reality, that doesn't work everywhere. If the sun were to burn out right now, it would take 8 minutes for us to find out, for light to travel from the sun to us. But in Newton's theory, it would be immediate. And so that's what's called instantaneous action at a distance. Einstein, in his theory, has a finite speed of information, and that's the speed of light. So that's the first problem that was fixed. The second is almost an embarrassing one, at least for me, maybe some of you. And that is when your teacher in elementary school taught you about gravity, she or he said, when you jumped up, the earth pulls you down, and you felt, okay, or the apple falls out of the tree. But did you ever ask why the earth pulls you down? I didn't, which I think is embarrassing, because it's the second problem, is that Newton not only had the problem of not describing finite speed of information travel, but he didn't describe why the earth pulls on you, why the moon goes around and is pulled by the earth. That's missing in Newton's theory entirely. In Einstein's theory, I won't describe it, it's a result of what we call the curvature of space and time that happens when you have massive objects around. And that is what causes the attraction of the moon to the Earth, or the RU when you're pulled down to the Earth. So Einstein fixed two problems that Newton had and gave a theory that was relativistic, which is what we need to do astronomy. So now let's go on with gravitational waves now that you understand Newton's theory's limitations. Okay, gravitational waves themselves are ripples in space and time. That's fancy words, but it's different than an electromagnetic wave. An electromagnetic wave, when it goes through space, is actually a form of particles, what we call a photon, or electromagnetic particle, that goes through space. When we talk about gravitational waves, it's really the words that you keep hearing, the distortion of space that happens due to gravity. In this case, it's a distortion of space, a ripple in space, that travels at the same speed as the speed of information, that is the speed of light. So in Einstein's theory, there's one speed, we call it the speed of light, but it's also the speed of gravity. And it's something that we've tested now, and it's pretty accurate. So it's a warpage of time and space. The reason the effect is so small, and the reason that Einstein thought it would be so hard to detect physically, is because space, now I'll use funny words because space to you is empty maybe, but space has a structure, and space itself, if we thought of it like a material, is very, very stiff. It's very hard to bend something that's very stiff, and space itself, in terms of the parameters, is very stiff, so the amount that you can distort it is very small, and so the effect is tiny. The key number for the experiment that I'll talk about is this number here, 21 zeros and a 1. So 10 to the minus 21. It's the same little h that I had in the formula on that difficult slide that gave the formula for a wave to go through space. So this small number is what the key is to see if Einstein's right or to actually detect gravitational waves. So what does it do? It distorts space and time. I'll show you how. Imagine that we had a ring with free masses around it. That is, the masses are free to be moved. They're just sitting there in space somehow. And the radius of the ring is L. And then a gravitational wave goes through. The gravitational wave, as I said, space is stiff, so it doesn't do very much, but it'll distort it, shown here. So instead of a circle, it becomes an ellipse with a change of length being this factor 10 to the minus 20, proportional to this factor of 10 to the minus 21. And depending on the frequency of the wave, it'll go back and forth between distorted vertically and distorted horizontally. So the effect is a little bit like when you go to an amusement park and they have these mirrors that make you tall and thin, short and fat, and you went back and forth between those. That's basically what we see happen physically, and basically what we have to find some way to measure. And that was the challenge for 100 years. Einstein wasn't stupid. He couldn't imagine that this could be measured because he couldn't envision modern lasers and techniques that have come along in 100 years. So using any sort of concept that you could imagine in 1915, it was certainly unmeasurable. I've written a little formula here on the size then. The size of this distortion, this little delta L, is proportional to this constant that's very small, the 10 to the minus 21, times how big the radius is of the circle. And so the effect is something like 10 to the minus 21 meters if I have a 1 meter circle. That's a pretty small number. And that's what we have to measure somehow. And the scheme that we use is called interferometry. It turns out that in physics, measuring something very accurate is always a challenge. And we have a whole organization in Paris that sets the standards and measures for how much a kilogram is, how long a meter is, and so forth and so on. And that gets refined with time. And it's very difficult to measure the absolute size of anything, whether it's the weight of a kilogram or the length of a meter stick. It's easier to try to measure the difference between two almost equal things. And interferometry is a technique, not the only one, but it's a technique that very sensitively can measure the difference between two numbers. And that happens to fit our need very well, because we're trying to see the difference between the radius horizontally and the radius vertically in this picture I drew of a distorted circle. When the circle isn't distorted, the two are equal to each other and the difference is 0. So that's the idea. This is then a picture of an interferometer. The light is shined from a laser, comes to a mirror, and is divided in two directions. And as long as the length of those two directions are equal, the light will go through as shown here. It's split in two, and it'll come back at exactly the same time. When it comes back at the same time, we can just set the interferometer such that they just cancel each other, shown here, and they go into a detector that sees nothing. If one of them becomes slightly, one of the paths becomes slightly longer than the other, as will be shown next here, then they can line up, or the phase changes the time it takes to come back, and we detect a signal. And that's the scheme that's used. It's a very sensitive scheme. The only problem is we have to do it much, much, much more sensitively than anyone's ever done before. We did not invent interferometry. What we did is determine how to make interferometers so sensitive that you can that you can measure this incredibly small number. So we want to do it. This is now a picture of the circle being distorted about 2 times a second, and we want to measure that difference. If I take the 10 to the minus 21, and I make the arms of the circle very long, that's why these instruments are very long. Then if I make it kilometers long, the distance that I have to measure is something like 10 to the minus 18 meters. So how big is that? That turns out to be about 1/1000th the size of a proton. That's really small. So we have to do interferometry to a very, very high accuracy. It turns out then that we figured we could do that in about the 1990s, using interferometry if we were careful enough, use enough tricks to be able to measure things well enough to do that. The key numbers were shown here. You have to do, this is an oversimplification, but it's really the challenges. There are 2 main challenges. One is that I have to be able to see the difference between the 2 arms to 1 part in 10 to the 12th, that's a pretty small number, the wavelength of the light that I use in the 2 arms. And that requires doing interferometry much, much more accurately than it had ever been done before. Many tricks were invented by a lot of different people, and we basically had in hand the idea in the early 1990s, and I'd say the implementation in pretty much by 10 years before we made the detection. We still had the problem, at least in LIGO, that we weren't able to handle the vibrations of the Earth well enough. So what are those? This instrument cannot just be put onto the Earth. If you have an interferometer and you use it in a freshman physics lab, you get an optical table and you bolt it down, and that's your interferometer. And that's fine if you're measuring some small shift from the wavelength of light, factor of 10 or 100 or something. But for 10 to the 12th, the Earth just shakes too much. And so we have to basically float the detector somehow so that it's at the frequencies we care about is isolated from the Earth. And that factor is about a factor of 10 to the 12th also. So we have 2 factors that we had to master in order to make this detection. The second one being isolating ourselves from the vibrations of the Earth. You can approach that in different ways. It's done somewhat differently in the Virgo detector, which I'll talk about briefly, than we did in the LIGO detector. But in our case, we basically tried to make as sophisticated implementation of something you use every day as possible, and that is use the same concept that goes into the shock absorbers in your car. When you go over a bump with your car, if you didn't have shock absorbers, it would bounce you up and down. But instead, with a shock absorber, it can't absorb the energy that's there anyway, but it takes the bump and makes it lower frequency, which is slow and doesn't bother you. So your ride is smooth. We want to do the same thing. We basically want to take any shock that's there, move it out of the frequencies that we care about, and basically then the Earth doesn't bother us. To do that, we made very special, just the right squishiness shock absorbers, and 4 layers of them independent of each other, and so forth and so on, and hung the mirror suspended, which I won't talk about. And altogether, that turned out, we didn't know, to be not good enough. So we maybe got a factor of 10 to the 10, but not 10 to the 12. We studied and looked for gravitational waves for 5 to 10 years that way. And then we added another technology, which I think is in the elevator speech, if you want, was the key to making the detection in LIGO. And that is, with the passive absorption in our scheme not working well enough, we added what we call active seismic isolation. So what's that? The best analogy is something that many of you have used also. When you take an airplane and you are bothered by the roar of the engines, you put out a few €100 and buy a set of these earphones that you put on your ears, and then the roar of the engines doesn't bother you. So what are those earphones doing? They're measuring the ambient roar of the engines and compensating for it, basically canceling it. You still hear the stewardess speak to you to ask you if you want coffee or milk or something. And that's because that's just a signal. It's not an ambient sound. So we have nothing to do with sound, but it's basically the same idea. So what we did was, inside this very sophisticated layers of shock absorbers, we put seismic detectors that measured the residual movement of the Earth that we were detecting, and we put activators in that pushed against it so that we compensated for that, and that gave us the last factor of 100 that enabled the measurement. I'll show that now in a couple slides. First, this is what limits these interferometers. We have, even though I made an analogy to audio when I talked about the airplane, we have nothing to do with anything audio. It's physical movements. But the frequency band that we're sensitive to is the audio band. Why is that? I suppose it has to do with the fact that evolution has basically decided for us that our ears should work where the Earth is quietest. So our ears are sensitive from about 10 times a second, 10 hertz, to thousandths of times a second. And for the same reason, basically, a gravitational wave detector, you put on the Earth, not in space, but on the Earth, is sensitive to basically the audio band of frequencies, but we're not looking at anything audio. So what's shown here, not going through them in detail, are all of the major problems that limit a gravitational wave detector. On the left, the shaded region is a region above all those that then is the sensitivity. You'll see on the left scale a number 10 to the minus 21 that's kind of on that scale. All this is a schematic drawing. As an experimental physicist, you usually like when you're limited by one thing somewhere, and then you beat that down. Unfortunately, we're limited by, by 3 things. That was to wake you up if you're flying. On the left is the shaking of the Earth, and you'll see it's very, very steep. It actually falls like frequency to the 4th power. On the right side is what we call shot noise, or a number of photons you have, and that's the same way that your ears are limited. They're limited by this, how much signal you can sample in shorter and shorter times. And in the middle, we're limited by what we call thermal noise. It's the fact for us that we work at room temperature. In future detectors, especially the one that's being contemplated here, the idea is to go to low temperature where that number will get much smaller. So the shaded region is where we're sensitive, and it's basically the frequencies in the audio band. This is a history of our detector, LIGO, from about the time we turned it on in the early 2000s for the next 5 years or so. Each starting at the top, it's the same scale. You can see it roughly has the same shape, and it keeps getting incrementally down. And each of those represent about 6 months or so of taking data. We're figuring out what limits us, licking our wounds, fixing everything that's wrong, putting in new innovations, running again. And fortunately, it keeps getting lower and lower and lower and lower. And eventually, it came down to a line you can barely see on the bottom, which is our design line. Once we got there, we looked for gravitational waves. This is maybe 27 or 8 or 10, and didn't see any. So even though we were more sensitive than anything that had been done before, we had new limits on the strength of gravitational waves, but hadn't seen any. At that point, we had to make improvements, which we had contemplated actually before we built the original version of LIGO, one of them being to put in these active seismic detectors. And we developed the technologies in between. So the top line there is the yellow-green line is basically the best sensitivity that we got in LIGO in this original thing. And then we put in the new isolation and several other improvements, better laser, a little different optics, and so forth. And the idea was to improve by a total of a factor of 10. A higher power laser, which was totally feasible, gave us a factor of 10 at the high frequencies. It's more photons, which is what you need in the high frequencies where you're sampling too quickly. In the middle frequencies, it's the fact that we work at room temperature, and we have to battle that, making a better suspension, a bigger test mass, help that. And at low frequencies, for us, it was adding the active seismic isolation. So the idea was that would improve us a factor of 10. We're very fortunate in this game because what we measure, this is again a little technical, but what we measure is an amplitude, not a power. When astronomers measure the signal from light from an object, it's generally the power. And so it falls off as the square of how far away it goes. Since we measure an amplitude, it's linear. If we can make a detector that's twice as sensitive, we see twice as far out, but that's 8 times as many stars and galaxies and so forth because it's the cube. So if we can improve a factor of 10, we actually improve a factor of 1,000 in the ability to detect gravitational waves. So we entered into this improvement program, and partway through it, we installed everything, but it's very sophisticated. You don't make it work as well as you design right away. We got to the point of the bottom line, and the improvement at high frequencies was, the improvement at high frequencies was just a factor of 3. A factor of 3 is a factor of 3 cubed, or a factor of 27 in our ability to see gravitational waves, so that seemed to us a good time to start. At low frequencies, the factor, because we put in a new technology, the active seismic, for us was a factor of 100. And that's 100 cubed, so it's a factor of 1,000,000 improvement in the ability to see gravitational waves at the low frequencies. That turned out to be the key for us, and it's the answer to a question I've been asked many times, which is how could we run for years with the original detector, see nothing, and then within the first week detect gravitational waves with the improved detector, and it's this huge factor at low frequencies. So we turned on the new detector, and within a week, we saw this signal. What's shown here is on the scale on the left is the 10 to the minus 21, the sensitivity you need. So the signal is about that size. The scale on the right is time, and the total scale is about 0.2 of 1 second. The two on the top are the two different LIGO detectors. I showed you two, one in the state of Washington, one in the state of Louisiana, and they saw this increasing wiggly signal. We call it a chirp signal. It gets narrower and taller, and then eventually stops. What that comes from is the in-spiral of these two objects that get faster and stronger and make this signal. What to notice is the top one and the second one look essentially identical. That's the first signal, that two detectors that are halfway across, 2/3 of the way across the US at exactly the same time saw this signal and it looked identical. So nothing that happens on the Earth is going to give identical signals at detectors that far apart. They're put on top of each other in the bottom slide, and you can see that you can, except for the little bit of color, you can't see very much difference. The little jagginess you see is because this is the limit of what we're able to do. It's got a little bit of noise, which shows the experimental ability. This is the only experiment I've ever done in my life where you didn't have to do any data analysis, which we usually do with big computers and blah, 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 and we do that in LIGO, to actually see a signal. So this was an astounding thing for a scientist to see this. For me, at 7 in the morning when I got up for breakfast. We detected it at 5 in the morning in Louisiana, which was 2 in the morning, 3 in the morning in California, so I was asleep. In the morning, this existed, and we saw the signal. And then we spent a lot of time trying to understand whether it was real or not. This shows the same two signals on the top, and the second line across is the calculation of what happens if these came from two heavy black holes merging into each other and colliding. And you'll see that they look very similar. One's calculated using fancy large computers and numerical relativity, and the one on the top is the experimental one. As an experimentalist, the way you immediately check your data is to subtract one from the other, and the third frame shows the subtraction, and all you see is just the jaggly curve, jaggly up and down, which is just the noise signal with no particular structure in it, which is the limit of our detection ability. So that's the actual signal. This signal, as it shows on the left, was on the front page of the New York Times and so forth. And then I walked down Madison Avenue at one point in New York, the fancy place where the fancy stores were. I turned my head and looked into a store, and there's our signal on a dress. So I knocked on the door, but this place was so exclusive that you just couldn't get in without an appointment, and no one was there. So when I got back to California, I got the number, and I called them, and there was some dress designer that picked this as a way to make dresses, and to make a thing that had been familiar because it was on all the newspapers as a design on dresses. So maybe it has some artistic scan too. Then she made one for us that was made into neckties that we wore in Sweden when we went. So that was kind of nice. Anyway, so what comes next? We detect these signals, and we want to compare them somehow with what astronomers see. We're looking at the sky now with gravity instead of with radio waves or optical or infrared or whatever's done in astronomy, like I started at the beginning of the talk. It turns out that black holes aren't supposed to give any sort of signal for optical, so we didn't have to worry too much. Nobody reported seeing anything, but we had the same problem. We want to know whether any instrument sees any signal in different wavelengths or different frequencies in the optical band. Somehow they can give us more insight into anything we're looking at. So we developed out of this the idea of doing a quick analysis that would be sent to astronomers for them to look and see if they see the same thing. After After working for 2 years on taking data, improving it more, we've reported to the world 10 examples of black holes, and now we basically have some idea of their characteristics. We're trying to understand where they come from. For example, they apparently, if we analyze that, I didn't show you, weigh about 30 times the mass of our sun, each of them. The combined final product is about 60 times the mass of our sun. Astronomers didn't expect such heavy black holes. Black holes come from a star, when it burns up all its fuel, collapsing because gravity that's in it causes it to collapse. But there aren't supposed to be stars that are heavy enough to make such heavy black holes. So where did they come from? That's a puzzle we're trying to work on now, and there's different concepts for where they might have come from. They might have come from some region of the universe where there's not anything heavier than, say, hydrogen and helium to make them break apart, and they're stable, heavier. Or maybe a part of the universe where there's lots of black holes, a dense part of the universe, where they eat each other up and build up into a heavy one. Or maybe they come from what we call primordial, or from the Big Bang itself, which to me is the most exciting, because we all want to know what happened really in the Big Bang. Okay, so that's where we are in black holes. We're now running again, and we have a lot of data. I can't talk about that yet. So let me go on to one other observation that we made before I quit. As we neared the end of this data run that I'm talking about, it was in August of 2017, so also 2 years ago. And at that time, the Virgo detector in Italy became operational and sensitive enough to be incorporated with us. And it enabled us, just by what we all know about triangulation, to tell where the signal came from in the sky much, much better than we could with LIGO alone. With LIGO alone, the accuracy is shown here in these big stripes for the earlier black hole events. Then when Virgo came, the little one down in the bottom is the accuracy we got. That enables us, if we can do that, to tell astronomers where to look, not just that we saw something in the sky, and that's what they need. So basically, we had that. Luckily, and no signals have ever been reported on those black holes from astronomers. But that happened just in time to see another signal, which actually was due to something quite different. And when we saw it merge, it wasn't just 0.2 of a second like the first event I showed you, but many, many seconds, 100 seconds, something like that. And so we knew it was something different. That has been analyzed to what are called neutron stars, 2 neutron stars colliding. That's different than black holes. It's nuclear matter, if it's neutron stars. Nuclear matter does give light, so you should see something also in electromagnetic detectors. We were lucky, not only that Virgo turned on just exactly then, but one satellite happened to be looking in that direction for photons in the sky at that moment, and they saw a signal in the same space. So that enabled us with confidence to tell the whole optical community that we saw something in gravitational waves. This satellite saw something in electromagnetic gamma rays, and essentially half the astronomical facilities in the world turned and pointed at some point to looking at this and analyzing it. And it's the biggest campaign in astronomy, I think, ever. And out of that came a description of this collision of 2 neutron stars, which matched, I don't know if it's exactly right because we have only one event, matched a theoretical or phenomenological explanation by a physicist at Columbia University called a kilonova. A supernova is the collapse of a star. This is called a kilonova, and it describes all the nuclear physics and what happens afterwards. And so we're looking forward to talking about more neutron stars as time develops. But as one example of an output of this, I'll explain one thing that's more general. So we're interested in all the nuclear physics in these extreme conditions, and we'll study that in the future. What's maybe more interesting to this audience is that we learned something about nature that's been a puzzle forever for physicists. And that is, in the Earth, we have heavy elements. We have, for example, gold, platinum, uranium, whatever. But the process by which we know that the universe created elements, most of the universe is made out of hydrogen and helium. We think the burning of stars, which is a fusion process, burns up first the hydrogen and helium, then the lithium, oxygen, and eventually up to iron, at which point it burns out, and the star collapses. So where did the heavy elements, really heavy elements, come from beyond iron? You probably care, and as I'll say in a minute. The idea then, because physicists always have to explain something even if it's wrong, is that the nuclear physicists made up a special process by which in the collapse of a star, when it burns up its fuel, it would have an enhanced production of very heavy particles, none of this proven anywhere, called an R process. And basically that was the only explanation until this observation. And in this observation, what we learned is that if you take this kilonova model, it's a very effective source for making heavy elements. We all know that we look at the periodic table and all those very heavy elements are there. They're there because we know how to produce them in the lab. They're produced by a lot of neutrons hitting a heavy element and making a heavier one. And then we get another entry into the periodic table. Well, what is more like that lab experiment than two stars made out of neutrons colliding with each other? So we learned that, for example, the majority probably, we can't tell for sure because we only have one event, of your favorite heavy elements, like platinum and gold that you wear on your fingers, actually came from a previous incarnation of a collision of two neutron stars, a new piece of knowledge. And in fact, it's very efficient at making this. The neutron star is a factory that neutron star collision made about 100 Earth masses of gold in one collision. So in previous ones, that's probably, or we think, that's probably now the best answer or explanation for how we got the material on Earth to make your gold ring. Let me end by giving you a glimpse of the future, and Stefan will give a talk after me that'll talk a little bit more specifically. The first thing is we're going to have detectors, not just LIGO and Virgo, but detectors several places in the world. This is going to give us the ability, if you look in the lower right, which indicates by the size of the little markers, how accurately we can tell where something comes from. So by the mid-2020s, it doesn't matter what and where something comes in, we're going to be able to tell where it comes from, and presumably alert astronomers and let them study it. Secondly, we know how to look at other wavelengths like the astronomers have. The best way to do that is to go into space and make an interferometer in space. This is a picture of an interferometer in space that's supposed to go up about early 2030s, called LISA, made of 3 different satellites shining the beams back and forth between those and measuring any distortion in the time by the passage of gravitational waves. That covers a very different frequency band. So what I've shown here is frequency like we did for electromagnetic, and to the far right is LIGO or Virgo. In the middle is the space experiment, so it gives you something very different. And to the left is yet another technique, which is called pulsar timing. So eventually, with gravitational waves, we'll cover all the frequency range, just like in electromagnetic range. Also, we know how to make what we have here much better. The key words for a physicist like myself is we're not limited by nature. So we did as hard as it is to do what we did, it's not limited by nature itself. It's limited by our own ability to make something technically better. And that we know various ways to make it better. For example, one key problem that I mentioned is that we work at room temperature. So bringing it to low temperature will make it better. Putting it deep underground, which is the idea here, will make the noise of the shaking of the earth much less. A different configuration is a technical question of how you can cover this frequency range best and singly with one detector. Cryogenic means low temperatures, and you can adjust it so it's optimized at lower frequencies or higher frequencies. So this is the next, what we like to call generation of making better detectors. We, as I say, are limited by the imagination and the implementation of physicists, not by nature in making the next generation detectors. And we'll hear more about that in a while. What does that do for you, just to end? It enables, if I just take the example of black holes that I just talked about, to lower the sensitivity from the 10 to the minus 21 that I was at before by 1 or 2 orders of magnitude. With these black holes, that'll enable us to see the ones that originated not just a tenth of the distance to the edge of the universe that we did now, but all the way to the edge of the universe. So what does that mean? It means we detect the ones that were made earliest or nearer the Big Bang, or do what we like to call cosmology. So for the first time, we can maybe use gravitational waves to study the earliest times, which cannot be studied with photons because the universe was too dense at early times, but gravitational waves go right through with the next generation of detectors. So I think we've just opened the door of something new. And the analogy I'll make is to Galileo. So Galileo, in 1610, for the first time, took the fact that lenses had been made to make eyeglasses, and he made a telescope out of it. He's not the first one to make a telescope, but the first one to make a telescope and then do something with it. And he pointed it at the planet Jupiter. So that was the first time beyond the naked eye that anyone had done astronomy with an instrument. He looked at Jupiter and saw that it had 4 moons. Now we know it has even more, but it had 4 moons. And that was the birth of astronomy. And we've seen what's happened in 400 years in astronomy. We've made incredible modern instruments, covered different wavelengths, learned about the evolution of the universe to a large extent, and so forth. And so what we've seen in parallel, in analogy to that, is Einstein basically coming out with the idea that you have gravitational waves. Using gravitational waves then maybe in the very first primitive way to see a couple of black holes collide, which we've done, analogous to seeing the moons of Jupiter, with the idea that we now have a completely new way to explore the universe. And invite me back in 400 years, like we've had in astronomy, and I'll tell you what we've learned. Anyway, have a great year. Thank you.